Hello, everyone. My name is Lun Lam. Welcome to the AIRS in the Air Multi-Robot System Lecture Series. The aim of this lecture series is to promote knowledge sharing and technological advancement in this field. And this event is also supported by the IEEE Robotics and Automation Society, Guangzhou branch, and Technical Committee of Multi-Robot Systems. And today is the fourth day of the lecture series, and we are honored to have two distinguished scholars who will be sharing their latest insights on multi-robot systems. Our first speaker is Professor Prorok from Cambridge University. I just listened to her keynote speech at ICRA early this month, and I find it very informative and inspiring. I believe that today's audience will also benefit a lot from her talk. And our second speaker is Malika Meghjani from the Singapore University of Technology and Design, and she is a distinguished lecturer of the Technical Committee on Multi-Robot System of the IEEE Robotics and Automation Society. I would like to thank all the speakers for their time and support for this event. And on the other hand, our today's host is Dr. Yuan Gao, and he is research scientist with AIRS, and he received his PhD degree from Uppsala University. And his research interest includes multi-robot system, reinforcement learning, and I hope that all of you will enjoy today's lecture. All right, Dr. Gao, over to you.
All right, thanks, Professor Lam. That's a very warm welcome and introduction. So let's continue with today's two talks. As previously introduced, the first talk will be given by Professor Amanda Prorok. She's an associate professor in the Department of Computer Science and Technology at the Cambridge University, and her lab's research focuses on multi-agent and multi-robot systems. Her mission is to find new ways of coordinating artificially intelligent agents to achieve common goals in shared physical and virtual spaces. She has been honored by numerous research awards, including ERC starting grant and ABB prize for the best thesis and EPFL. Let's continue with learning today's topic on learning cooperative control policies for multi-robot systems. And Professor Amanda Prorok, up to you.
Thank you very much for the kind introduction. It's a real delight to be speaking today here at your distinguished lecture series.
So Professor Malika Meghjani is an assistant professor in computer science and design pillar at the Singapore University of Technology and Design. She directs the multi-agent robot vision and learning lab with a focus on algorithm design for efficient, reliable, and scalable robots that can work independently and collaboratively with humans. Her research interests are in planning under uncertainty, reinforcement learning, computer vision, and deep learning. The applications of homework are in field robotics, especially for the underwater and the surface vehicles. Malika has been cited by the Analytics Insights in 2020 as one of the world's 50 most renowned women in robotics. She has won different awards from McGill's Google Antenna Brock, and then Canada Women in Engineering. So let's welcome her for the talk named Real-World Applications of Heterogeneous Multi-Robot System. All right, Professor Meghjani, up to you. Yeah.
Thank you so much, Yuan Gao. And thanks for inviting me today. It's very exciting to hear the talk with Amanda, and I hope we can continue that kind of theme in my talk too. So I'm also going to focus on heterogeneous multi-robot systems today. And as Amanda kind of described a bit on like having same observations but different actions by the robot, we do consider such heterogeneity as well in the multi-robot systems that I'll be kind of focusing on today. In addition to that, we will also look at heterogeneity in the hardware sort of domain, and I'll kind of highlight both in terms of how these real-world applications change in terms of hardware heterogeneity as well as capability heterogeneous robots. So let's get started on that. To give you an overview of what we do at our lab, our objective is to develop technologies of autonomy for multi-robot coordination, search, and planning. Using vision and learning algorithms, specifically in various domains that you can see here on this slide, going from aerial domain to land and as well as marine domain. So our interest has been broad in terms of the application space, but the underlying objective is to sort of focus on vision and learning algorithms to be able to apply them in these domains to come up with useful applications in real world. Right. So I would like to take you a bit back in time where I started my journey in heterogeneous multi-robot systems in marine domain specifically, where we were interested in monitoring underwater environments, especially coral reef monitoring. So this work is almost it's been a decade now already. It seems like yesterday, but this was what we did during my grad school. Sorry, yeah. I hope the video is playing fine at your end. But yeah, this work is specifically looking at heterogeneous robots from the aerial domain to the surface domain and underwater. And the objective here was coral reef monitoring. So given that there are communication constraints underwater and we are not able to establish that communication link with the underwater vehicle, we had this specific behavior that the underwater vehicle would surface up to the water and sort of rendezvous with the surface agent to meet at specific locations to get the command task over, handover. So here you can see there is a remote biologist sitting in another country completely and kind of giving that locations of interest to the aerial vehicle, which is providing the bird's eye view perspective. And these coordinates are sort of like relayed down to the boat on the surface. And the underwater vehicle has to sort of meet or come together with this surface boat to kind of collect those coordinates and then go back down at those locations to get a close-up look from that. So though communication is there in these things, but our interest in these sort of problems are where we actually need to have rendezvous or meeting point between two different robots. It can be in the same domain or in different domains. It can be between robots with same capabilities or robots with different capabilities. Here you can see it was the rendezvous point was between the surface and underwater vehicle with different capabilities in different domains. Right. So again, this was more of a proof of concept that we were trying to show over here that we can send down a team of robots and sort of help a remote biologist to get the data as to where on demand they want to survey. Yeah, but this was like one-off attempt and this remains state of the art. And still, I believe it's the state of the art in terms of how heterogeneity can work from different domains to do coral reef monitoring specifically here. So here you can see the annotated results by the marine biologists that were done. So there were certain challenges that sort of got highlighted during this set of experiments. And I wanted to kind of go through them one by one with you guys and specifically share what insights that we were able to identify. So the first of kind of problems that we are looking at is where we want the robots come together for information exchange. So these are the problems where you can't just communicate with the robot across the field, but they need to actually come in either line of sight or come close to each other in the vicinity of each other's communication range to kind of do the information exchange or knowledge exchange. So the first important task here or the challenge was to dynamically identify rendezvous locations in either unstructured environments like you saw, or in structured environments where the possible meeting points are even further constrained. So I will highlight each of these applications in the upcoming slides. Secondly, what we also identified was task allocation needed to be done in a decentralized and dynamic manner so that the robots had more independence in terms of task execution. And lastly, in order to robustly validate these coordination strategies, we needed a way of going from sim to real environments so that we can kind of translate what we are learning in simulation into the real world as well, with a smooth transition between the two. Right, so to kind of address this again in terms of the rendezvous meeting point, we looked at marine domain for the problem of data collection. The specific problem that we were looking at was passive drifters that are cheap in their cost as well as very small computing power on board were deployed in large numbers, and they did not have any active propelling unit on them. So they actually drifted away with wind and current. It could collect data for a longer period of time, but the idea here was to be able to gather data from these little devices because they had limited memory or limited power on board. And yeah, we had to kind of collect the data to kind of get inference of what's happening on the water environment. So these can also be kind of applied to other applications such as search and rescue in a disaster scenario, or search and track of sea creatures in order to count them or figure out where the numbers are increasing or decreasing, right? So the first step for us to kind of get to the point of rendezvous or kind of figure out where to kind of meet these little cheap drifters to collect data from them, we had to sort of do modeling as to modeling of the trajectory of the target specifically. And this was based on the wind and current data that is provided. So you can see over here in the animation on the right side, we are looking at real-time wind and current data. And based on the physical properties of the target, we are able to sort of estimate as to where the target trajectories can be next. And using such information, we can sort of draw as to where the potential meeting points can be. So this sort of gives us a coarse information about where the trajectories can be. But once we get into the vicinity of those target regions, we can do an exhaustive search. Specifically here, we looked at spiral patterns in the marine environment again. And these spiral patterns sort of gave us the scenarios where what is given the speed of the robot as well as the speed of the target, will we be able to sort of rendezvous with these targets in time? So the idea here was to be able to figure out sort of like a threshold as to when we can say that the targets are permanently lost and we can't able to catch up with them. We aren't able to catch up with them. So using some theoretical analysis as shown here, we were able to come up with that upper bound and say that, okay, beyond this speed limit, the robots will not be able to catch up with the targets and should stop the search at that point. So at least we were able to guarantee the time of failure, if not the time of capture. Right. So in this work, we sort of like applied that metric and used spiral search patterns and some other strategies along with it to kind of find these targets, get to their location, and get the information out of it. Right. So here's that animation where there's drifting target, and here you can see in the field itself in the ocean environment where the drifters are, and the surface boat is sort of like trying to figure out which is the best location to rendezvous with the target that has floated away. So after several iterations of search, it's able to sort of spiral down to the target and be able to communicate and get the required information out of them. Right, so these can also be survivors from a disaster scenario where the finding the target is a must. And here we can see that using different search patterns, we were able to sort of find the target, looking at two optimization criteria. One was guaranteeing the target search, and also secondly, optimizing on the time to find the target. So we want to be able to find the target as soon as possible, as well as be able to guarantee that the target will be found. So those were some of the results here. Are we showcasing? So moving on from here, we also actually looked at the problem of rendezvous between different domains of vehicles on land. And here you can see that we're able to look at an application which goes from the first mile to the last mile. So in the first mile, they are smaller vehicles such as scooters and golf buggies that are autonomous in nature. And we want to be able to sort of channel through the passenger's journey from the first mile to the last mile so that the passenger can get off from these first mile vehicles and get on to the car which can go on the road. Specifically, this problem is in a structured environment like in road network, where the rendezvous meeting points are much more constrained and cannot be just in the open field environments that you saw in the previous application. So here, it was very important for us to have a good fast computation time in order to find these rendezvous locations dynamically on the go in an online manner. So our contribution specifically here was in terms of finding these dynamic rendezvous points between different domains of vehicles, and as well as routing the vehicles in the network in a congestion aware manner. So to kind of give you an overview of how the application looks like, here's what's happening. The human is sort of asked for a ride using a mobile phone app, and then the vehicle has come to the human. Again, these need to be accessible points where the human can come to the, hop onto the vehicle. And from here, it navigates into the pedestrian environments. Of course, there is a lot more things happening in the background in terms of object detection, tracking, and also prediction of where the targets are going to move next. And then based on that, there is planning happening in terms of movement of the vehicle itself. But what's interesting and what I want us to focus here is on the rendezvous meeting points where the vehicle sort of progresses further. Sorry, I'm going to speed up the video. So here the vehicle moves out from the first mile and comes to the location where the user can actually transit from the autonomous golf buggy to the road car and continue on to the journey. So that's what we are again looking out for over here, wherein the communication in the sense need to be quite close to each other in terms of here the communication is defined as within the line of sight or within the reach of being able to transit from one vehicle to the other. And for this purpose, the two vehicles have to come quite close to each other in the vicinity, right? So specifically here, we actually looked at figuring out these dynamic rendezvous points in real time. And we applied certain algorithms where we took some heuristics in terms of calculating the distance between the target locations and the source where the vehicle is currently, and then being able to use that information to sort of calculate where would the fast meeting points can be analyzed. So once these meeting points are analyzed or selected, we are able to kind of pick those meeting points and then do the transition between the first mile and the middle mile. And the same process sort of like happens at the other end of the vehicles as well. So it's very important over here so that these transit points are selected dynamically and in real time, so that the entire coordination strategies can happen in a time efficient manner. Right, so that's the first challenge that we kind of looked up close in terms of heterogeneous multi-robot systems, where we wanted to make sure that the rendezvous points are selected in a meaningful way, as well as the entire coordination strategy can happen in a time-efficient manner. Secondly, we wanted to focus on the aspects where the humans are working closely with the agents on field. And here we want to specifically look at the problem of urban reconnaissance, where let's say the here the guiding agent is the drone that is sort of like leading the human to get to the exit point as fast as possible and with least obstruction as possible. So there are conflicting goals over here in this particular application where the agent needs to kind of get to the exit point as soon as possible, but at the same time, it needs to weigh in or wait for the human to catch up at the points of conflicts or at the points of uncertainties. Let's say it's in the corridor or where the obstacles are in way of the human and human needs to navigate around it. So we formulated this problem as a nonlinear model predictive control. And here you can also see in a small lab setup where we have the drones leading the crazy fly drone leading the path for the ground vehicle, which is actually being controlled by a human. So here we sort of kind of showed that using the model predictive control, we were able to do this urban reconnaissance application successfully. So that was what we had done using an optimization-based approach, but we also looked at learning-based approach where we have adversarial targets that are running away or like flying away from the agents that are tracking them. So these agents are again heterogeneous in nature in terms of their capabilities now. So we want the agents to be able to look out for new targets, at the same time capture the existing targets that they have identified. So traditionally, such an approach is based on traditional swarming-based behaviors, where you have to manually design these behaviors. But what we wanted to do is to learn them on the go in a decentralized way. So here you can see that at the execution time, the controls are in a decentralized manner, and we are able to sort of deal with dynamic environments as well as dynamic targets. The targets are not just fleeing away, but they are also learning on the go, meaning that every time they encounter a situation wherein they are too close to the agent that is tracking them, they kind of learn to evade away from them. So this was the challenging task that we wanted to tackle using a learning-based approach. And here we sort of went with the policy gradient method, where we had, as I mentioned, two different roles of the agent that are pursuers and the scouts. So the pursuers actually are pursuing for the adversarial targets, and the scouts are looking out for new targets in the environment. And using the state information and the communication between the agents, which is also getting adaptive on the go, we were able to track the targets at the as fast as possible, and as well as spread away into the environment as much as possible. So on the left is the traditional policy gradient method using MADDPG, where we sort of like had very close encounters between the pursuers and the targets. But at the same time, the distribution of these pursuers in the environment was not as great as opposed to what we kind of portrayed here in a role-based approach, where the agents have two different roles of pursuing the target as well as scouting for new targets in the environment. So you could see that there was a nice spread of agents in the environment while this execution was happening. So here's a quick video for showcasing that, where again the annotations will come up while we watch the video. But there is one target at the far end, and they are pursuers here, scouts and pursuers here in this region, which are able to kind of drift through and get as close as possible to the target, as well as spread across in the environment to be able to look out for new targets, right? So on the bottom right, you can see the OpenAI simulation rendering. And on the right side, we were using UWB to kind of track the target's position or even other agents' positions. And you can see the trajectories evolving over time. So the green is the target at the further end, and the pursuers kind of get like very close to them. That's a definition of capture in our problem. And the scouts, you can see that they are well spread out in the environment and are able to look out for new targets that might appear in the environment. So that's the learning-based approach that we kind of looked out for. And here we wanted to kind of highlight that decentralized and dynamic task allocations can significantly improve the real-time performance of the coordination strategies, and some applications that we kind of showed in the real-world application as well. So the last part, I wanted to sort of focus on the sim to real aspect of heterogeneous multi-robot systems, where we want to be able to come up with a realistic environment simulations that we can easily translate back into the real world. So in this work, we sort of focused a bit on coming up with robust simulators like these, which are kind of based on the real world. So we can actually scan the real world environment, bring that into the simulation environment, and then execute all the algorithms using that. We were able to sort of make a bridge between the Unity environment where the simulator was built, and as well as use raw space algorithms to kind of plug in all the simulated robots. And then easily we are able to translate these raw space algorithms into the real world based on real robots as well. So we were able to bring in these high fidelity robot configurations as well into simulation and then execute that. So here's the overview of system overview of our approach, where we have the Unity environment and the ROS environment being bridged together. And what we were able to kind of work out here are some basic fundamental actions for the robots, which are specific to aerial robots as well as the ground robots, as you can see in the slide. So I'll just give you a rundown, the quick demo of how the simulation runs. The specific contribution in this work was on the simulation development itself. And the simulator is open source as well to the community. So if you would like to use it and see for yourself, the link is provided up there on the top right. And here you can look at the scenario where there are 2 drones that are deployed. There are also ground vehicles in here. The environments that we considered are also indoor and outdoor environments with robots and humans as well as in loop. The human also gets to input the commands using a chat interface where using some fundamental command language, the human is actually able to give in commands to the vehicles as well. So this is in the outdoor environment. I would like to transit a bit into the indoor domain and show you that as well. So again, these are the views on top from the aerial vehicles, and this is from the human operator and the ground vehicle. So as the mission progresses in different rooms, these information are also shared out. There are few good features that we came up along while developing the simulator itself, and I'll kind of highlight that briefly in the next few slides. So as I mentioned, one of the key contributions was to be able to bring in the real world into simulation. So on the left is how the real world look like, and on the right is the simulation setup within our simulator. And this did not take a long time. This was pretty fast for us. In matter of few minutes, we are able to import the real world into the simulation, and also have equivalent robot models in there to kind of translate that. So here you can see the simulator and the real sort of side by side each other. In addition to existing obstacles in the environment, we were also able to insert new obstacles and be able to work through that. So if just to highlight some of the features that we kind of worked in is we were able to replicate the virtual environment using the importing the real world. We were able to dynamically place obstacles in the environment in addition to the existing obstacles in the physical world, so that we can strategically run various coordination strategies and then see which ones work best in different scenarios. We also came up with modular robot actions, which we can sort of build on and then build more complex behaviors on top of it. We had a little chat interface, as I mentioned during the slide related to it, that the human can also give inputs on the go. And then finally, we were able to sort of validate this multi-robot heterogeneous teaming with robots in different environments as well as the human in loop, right? So that was another essential learning for us, where heterogeneous multi-robots, we were able to greatly benefit for strategic high-level planning. So we could run variants of the real-world environment with different scenarios, different placement of obstacles, and then kind of see how which strategy worked best for robust validation, right? So to kind of sum up all that we talked so far, we were interested in looking at the coordination problems where rendezvous is very important. And we kind of showed that if the rendezvous points are wisely selected, then they can result in time-efficient coordination strategies, as well as the dynamic task allocation and decentralized task allocation can help with real-time performance of the team. And then finally, the need for a simulator which can bring in the real world into simulation and then translate back the learning from the simulation into the real world to kind of close the loop is also very important, especially in terms of heterogeneous multi-robot systems. Right. So with that, I would like to thank the team which has done most of the work that I showcased here today, as well as the sponsors and supporters of our work. With that, I also want to say that we have openings at the lab. So if you're interested in joining us, please feel free to reach out. Thank you so much.
Great. Thank you, Professor Meghjani, for your interesting talk. And now I have two questions. It's a very ambitious project that you want to build a different kind of robots and the human into this simulator. Do you have a plan to have dynamics also implemented in your simulator, or just want to have more like kinematics or high-level interaction in your simulator?
Yes, so the simulator currently does have the dynamics in there, but that's not so much of a contribution. There are existing ROS framework that we imported into it. But yes, the idea was to be able to kind of strategize high-level planning using the simulator, but the low-level controls sort of like remain same based on the robot model that we are executing on. So basically, when the user uses our simulator, they don't need to worry so much about the low-level planning. They just need to focus on what high-level coordination strategies that they are looking at. So yeah, if you're building a reinforcement learning algorithm, how do you sort of plan under uncertainty as to which robot should go where in a particular strategic scenario that comes up there? Yeah.
So you also mentioned that you worked with underwater and surface robots. Do you have a plan to include them into your simulator, because it's much very different from the rest of the robots, like Iron ground vehicles?
Yeah, so it's a bit tricky in terms of like building a simulator for it, because what we are interested in specifically on the surface of the water is how wind and current data can influence that. And that's something tricky to kind of implement within the simulator. I believe if we can, like in our current work, we are using real world wind and current data and then applying it on the physical properties of the target. I think that's sufficient enough for us to kind of work, and we are still very close to the real world scenario. So I think if you had a choice of using the real world data, I would go for that rather than building a simulator which kind of approximates these sort of forces.
I see. So let's now take some questions from the audience. Okay, the first question is, thank you for your excellent talk. I observed that you employed both optimization-based and learning-based approaches in multi-UAV application. Could you share the benefits of these two methods within this particular application?
Right. That's a great question. Thanks so much for bringing it up. Yeah, I think like in the optimization-based approach, it's much more easier in terms of like applying the optimization techniques out onto the physical robots. There is, of course, the whole training time is forgiven. Like there's no training time for it. You could like directly deploy it and see how it works out. But having said that, learning-based approach has its own merits in terms of like evolving behaviors, right? So some of these behaviors we don't have to kind of manipulate and hand tune it, whereas yeah, the agents can learn this on the go depending upon where the obstacles are and how the reward function sort of spans out. So I think they both have their respective merits in terms of like one is the computation time for optimization-based approach, or like learning time for optimization-based approach, versus the fact that the behaviors are much more evolving in terms of learning-based approach. Yeah.
Okay, I hope that answers the question. Let's see, is there any more questions? Okay, while we wait for the questions, I also have this classic question that I just asked Amanda. What is your definition of heterogeneity? Like,
yeah, so I definitely agree with what Amanda mentioned there in terms of like heterogeneous agents would have the same observation but come up with different actions. So this would be the case for even the robots in the same domain as well as robots in different domains which are physically different from each other. So I further kind of like want to highlight a bit more distinction in there. So one can be heterogeneity in the capability sense, and the other one can be heterogeneity in the physical form itself. And both of them will have the same definition or comply to the same definition that Amanda also mentioned, that for the same observation, they will have different actions because of their physical hardware differentiation or because of their capabilities that they have. Yeah.
All right. Okay, we get another question. Hi, Professor Malika. May I ask whether the simulator you introduced can realize online modification of the configuration of the robot or the connection relationship between different links of the robots? If not, do you have any suggestions for implementing this function or modifying configuration online? This function requires maintaining the state of the robot's movement speed, but the kinematics relationship of the robot itself will change.
Right. So right now the simulator cannot do that online, but yes, it's the way we have like set the simulator is that there is an initial script with can take in all the parameters that you want. So perhaps if you could store the final stage of the simulator that you want to kind of continue from, that can be the next starting point in the next iteration if you would like. But yeah, right now there is no like simple way of online reconfiguring it, but instead you have to go through the scripting method that I just explained.
The simulator is based on Unity, right? Or...
Yes, that's correct. Yes.
Okay. So yeah. Okay. Well, we wait for the questions, and I have another question.
Yes.
So I noticed you used this people, human in your simulator. So to what level it can mimic like a real human? It's just a path planning, or it's also like social functionalities?
No, it's simple path planning. In fact, one of our first versions of the human was actually a robot. So it had a body of a human, but it actually was doing path planning of the robot. So I mean, again, it was not the focus of our proposed simulator. But again, since it's like a ROS Unity bridge that we are incorporating, on the ROS side, you could plug in any model of the human behavior that you would like. So it's quite modular in that sense. So you can plug and play whatever you would like to work with.
I see. So, all right. Let's see. Is any more questions?
I think it's
okay. So I think that's all the questions that we received. And thanks again for the interesting talk. And,
thank you.
Yeah, thank you. So
thank you for inviting.
It's all right. It's a very interesting talk. So, all right. So I guess today's talk is finished, and we'll continue our series, module series, maybe later. And thank you again for all the audience that joined. And all right, bye.